Hi, this is Andrew Bunnell, and I'm going to show you a little bit of data from the Earth-filled NMR and describe how this data may interfere with some of your measurements. The first thing I'm going to, and then I'm also going to show you how to take FFTs in Origin. So the first thing you got to be able to do is be able to capture the data and put it on a jump drive or in some other form so that you can take the data from the oscilloscope and then put it onto another computer and you can run Origin. This is Origin2016. And this was an example of some data that I just took, and I noticed that there was a bumpy pattern. And I wondered if there's some bleed over from 60 hertz, and I wondered if the 60 hertz bleed over signal was mixing with my signal from my Lamar frequency, from the spin down or the relaxation of the protons, and if those two were mixing in such a way that it was creating a beat pattern. So let's see how we can go about doing that. This is the data that's plotted from that, and then to do a Fourier transform, this right here was the time data from the oscilloscope in seconds, and this was amplitude in volts, and I took 50,000 points, and I had a little small offset so that when I look at the data, I like to have that little tell right there, but it's not needed. And then what you need to do is make sure your time column is an X and that your Y column is a Y. And you do analysis. Okay, let's move this down. Analysis, signal processing, FFT, open dialog. And then this dialog window opens up right here. And you don't need to really change anything except for, to simplify it, what we're going to do is we're just going to do only one plot of the magnitude because we're only looking for the magnitudes at particular frequencies. And I'm going to go ahead and hit OK, and it brings me to this data right here. Now, I already plotted this data, but let me go ahead and plot it again. There is a lot of data for 50,000 points, and so I'm going to do that, and then I'm just going to plot the dots with symbols. And it says there's speed mode on because we got a lot of points of data here. So to turn speed mode off, I know my signal is roughly from 1800 to, well, it's roughly, I know where my signal is. Okay, so I'm going to first off change the symbol size to small. I'm going to go to layers, speed size, and uncheck worksheet layers. That's going to make it run slow for just a second. Now I'm going to double click on the x-axis, and I know where my scale is, and so I'm going to just go to 1800 to 1900 so we can see a nice wide area of my peak. Hit apply, hit OK, and now we have these two peaks. I'm going to go ahead and use the magnifying glass on the side and just zoom into this little area. Next, I'm going to use the data reader tool and click on the top one, 1852.5 and 1859.5. That sounds awfully a lot like 1860. So on this other graph, I went ahead and already put those numbers. And here I'm showing that the amplitude is also roughly 1/2. And I put my uncertainty as 0.2 hertz simply because if I click 1 point bigger, 1 point smaller, it's 0.2 hertz. Now, technically, you should be using standard deviation for that, but just as a rough estimate, I put 0.2 hertz. All right, so now, using those numbers, using those frequencies that I've found, and using this difference in amplitude, I created two sine functions. Let's go back to my data and go to this worksheet. So now in the same worksheet, I've created two sine functions, or cosine functions really, where it's taking the time column, and I just scaled it to 1. I could have done a scaling factor based on the number of points taken and the number of sine waves fit and all that kind of stuff. Just basically the Fourier transform, but I'm just scaling that to 1. And here's my formula, cosine 2 pi over column D, divided by my period, which is just the inverse of the frequency. Same thing over here, and this time I'm going to do 1/10 of that 1 because it's twice the sampling rate, and I'm just normalizing it to there. And same thing, except for now I'm going to do 1860. I could have put 1859 right there, but that's what I did. And then I just added the two columns together and put it against, plotted it versus time. And when I did that, I found, let's see, oops, that was my new graph that I just created. I found this graph and I zoomed way in just on the first couple beats. And, well, I took my cursor and measured a point there, measured a point there. Now this doesn't show the exponential decay like the other chart did. I didn't include that as a varying amplitude. But here's a sum of two sine waves. And the difference of these two were 1.26. And the difference of the other graph was 1.426. And that's under 10%. So for very crude, rough measurements, I think I can say that this beat pattern that you see is based on a multiple of the 60 hertz line coming in, which I didn't consequently measure. So the 60 hertz can vary by a small percentage. And so if I even change that by a small percentage, I may have got a different number. Although, honestly, I guess I could have gone back to my Fourier transform and said it was off by very, very little based on the Fourier transform. And so if you notice bumpy data, when you're taking your data, it might just be close to a multiple of AC line. And that's it. Thanks for watching.